On a fait une erreur sur l'information. J'ai vérifié, on n'avait pas fait d'erreur. On va changer. You are in Berkeley, aren't you?
Yeah, I'm at Berkeley.
Okay, thank you. Ouais, tu peux passer. Qu'est-ce que tu veux faire? Non, non, tu le laisses là, tu le poses là. Non, ça va, vas-y, vas-y. Une minute, 1 more minute, and I'll stop. Okay, welcome everybody for this last lecture of the day, and we have the pleasure to listen to Yi Lei from University of Berkeley, and she'll talk about steady gradient Ricci solitons with positive curvature. Please.
Yeah, thanks for the invitation and the introduction. So today I'm going to talk about some new examples of steady gradient Ricci solitons with positive curvature. So these solitons in dimension 3, they are known as the flying wings, as called by Hamilton. So here's the structure of this talk. So first I will introduce some previously known examples of steady Ricci gradient solitons, and then we'll state the main results. And also we want to compare our discoveries with those that we know in mean curvature flow. And then in the second part, I'm going to show you how we construct these steady gradient solitons. So there's a uniform way to construct these solitons for all dimensions n greater than equal to 3. And then in the last part, I'm going to show you that in particular in dimension 3, that these solitons we constructed are flying wings. So this is the structure of the talk. So now let me get started. So the Ricci flow equation is introduced by Hamilton in 1982, and it is a family of smooth metrics evolving under this equation. So the derivative of the metric is equal to -2 times the Ricci curvature. And so among all the Ricci flow solutions, we're particularly interested in those that are self-similar, because those self-similar Ricci flows, they often arise as singularity models for compact Ricci flows. Okay, so here are some elementary examples for those self-similar Ricci flows. First, you can look at this two sphere, and then if you evolve it by a Ricci flow, and then yes, this Ricci flow will shrink this sphere to a point, because the Ricci curvature is equal to 1 times the metric. So the right-hand side in the equation is positive. It is negative. So this metric will keep shrinking itself until it becomes a round point. And as a singularity model of this sphere, if you blow up at a singular time, then you will see again this shrinking sphere itself. So it is a singularity model of itself, this shrinking sphere. And then you can run a Ricci flow on this on a flat torus. Then the right-hand side is 0, so the metric does not change over time, and so it will. So this will be a static Ricci flow, and then in the hyperbolic surface, you can also run a Ricci flow, but this time you get a positive constant on the right-hand side. So the metric will expand itself and get larger and larger. And so this Ricci flow will be defined for all positive times. And at time t goes to 0, it will get a singularity. And you blow up the singularity and you see this solution again. So it is a singularity model for itself as well. So these three examples are they are all Einstein manifolds, and they are self-similar Ricci flows. And even more, we can generalize this concept to a broader class, and that is called the Ricci solitons. Okay, so Ricci soliton is a complete Riemann manifold. If there is a smooth vector field X such that this equation is satisfied, so Ricci minus 1/2 the Lie derivative is equal to some constant times the metric. So if your vector field is 0, then you don't have the second term, then you will just have the Einstein manifold. So it is a generalization of the Einstein manifold. And this lambda is some fixed constant. If this Ricci soliton is if this vector field X is even given by some is even equal to the gradient of some smooth function f, and then we say that this Ricci soliton is a gradient Ricci soliton, and we call this f to be the potential function. And so in this case, the Lie derivative of the gradient is equal to 2 times the Hessian of the function. So now the second term becomes to the Hessian of f. So the gradient soliton equation is becomes this one. And also as before, we can generate a self-similar Ricci flow using these Ricci solitons in this way. Okay, so if you have a G0, which is a soliton metric, and the lambda is the soliton constant, that's lambda here, then you can define a family of metric GT by pulling back this G0 using a family of diffeomorphisms generated by this rescaled vector field, where phi 0 is the identity, and you rescale this metric properly, and then you can check directly by computation that this family of metrics GT satisfies the Ricci flow equation. And so this will be a self-similar Ricci flow because every time slice GT is isometric, modular this rescaling and modular this diffeomorphism. Okay, so for different constant lambda, you will see different types of Ricci flows. For example, when lambda equals to 0, then you do not have any kind of rescaling here. So your flow is defined for all positive and negative times, and that is called an eternal Ricci flow. And if lambda is positive, then your solution is defined for all negative times, and in that you get an ancient Ricci flow. And for lambda, which is if lambda is smaller than 0, then your flow is only defined for all positive times, and that is a immortal Ricci flow. Okay, so depending on if lambda is positive, negative, or 0, we divide them into 3 different types of solitons. First, we have the shrinking soliton if lambda is positive. So as we've seen before, it includes all the Einstein manifolds of positive scalar curvature. In particular, the shrinking round sphere when n is greater than equal to 2. Another interesting example is the Gaussian shrinking soliton. So this soliton is the Euclidean metric on Rn, which has the flat curvature, but the potential function is a quadratic function. So you can check that this soliton, even it is flat, it is also a shrinking soliton and satisfies the shrinking soliton equation for some lambda greater than 0. And then if you take product of the second and the third example, then you get some shrinking one cylinder. So it is also a shrinking soliton. And when lambda is less than 0, we have the expanding gradient Ricci solitons. And the first we seen before is the Einstein manifolds of negative scalar curvature, and in particular the hyperbolic surfaces. And the second class of expanding gradient solitons I want to mention here is a theorem by Alex Diriwal, and he shows that for any n-1 dimensional Riemannian manifold, if it has curvature operator bigger than 1, then there is a unique expanding gradient soliton with positive curvature operator, and that is asymptotic to this to the symmetric cone over this n-1 dimensional manifold. And to make it to be unique, we have to require that at this critical point of f, the scalar curvature is equal to 1. So this is actually give us some way to construct many expanding gradient solitons as long as you have some n-1 dimensional manifold satisfying this curvature lower bound. Okay, so later I'm going to show you that we're going to use this result to construct some proper expanding gradient solitons, and then we're going to take some limit and get the static gradient soliton that we want. Okay, but we'll come to that later. And then the main focus of this talk will be about the static gradient soliton, which corresponds to lambda equals to 0. And so in this case, you have a very simple soliton equation, the Ricci equals to the Hessian of f. So when this potential function f is just a constant, then you have all the Ricci flat manifolds. So this is not something very interesting in here. So the first non-trivial example would be the two-dimensional cigar soliton, which is constructed by Hamilton. So this cigar soliton is a metric on R2, and you can write down the metric in this form, and this is its potential function. So okay, so this cigar soliton, all I want to say is that it is rotationally symmetric. It looks like in this picture, and P, the rotationally center, is also the critical point of f. So this is the potential function. And also the cigar soliton is collapsed. So by this I mean that okay, so it is collapsed, which can be seen as below. So if you take a sequence of points going to infinity, and you consider the limit of this pointed manifolds, then it will converge. It will converge to S1 times R. It will converge to a flat cylinder. So the flat cylinder has 0 curvature, but it does not have Euclidean volume growth. So this one is collapsed, which implies that the cigar soliton is also collapsed. Okay. And then another thing about the cigar soliton that is important is that, okay, so it can be written down as a warped product metric since it's rotationally symmetric, and this warping function is finite, and it has a finite limit as r goes to infinity, and this is scalar curvature. Scalar curvature decays exponentially fast. The decay rate is uniquely determined by the scalar curvature at the tip. Okay, and so this is a cigar soliton, and as it is collapsed, it is not any singularity model of a compact Ricci flow. But if you consider long-time Ricci flow, you probably will see the cigar soliton as t goes to positive infinity. So it's still important. And then next, for higher dimensions, the cigar soliton can be generalized to another class, which is also rotationally symmetric, defined on Rn, and these are called the Bryan soliton. So here's a picture for the Bryan soliton, and the cigar soliton, it is rotationally symmetric around the critical point, but it opens up much faster than the cigar soliton. So if you write down the metric as a warped product metric, then this warping function increases like square root of r, and equivalently speaking, the scalar curvature decays like 1 over r. So you have a linear curvature decay. Okay, so this is for the Bryan soliton. And this Bryan soliton is an important singularity model, since you, as you probably seen in Richard's talk last week, this Bryan soliton is a singularity model of the degenerate neck pinch. So one can actually show that for a three-dimensional Ricci flow, which start like this. So it will evolve and run into a singularity, which is modeled by a Bryan soliton. Right. Okay, so so you can easily check that this Bryan soliton is non-collapsed, because in this case, like before, we take a sequence of points going to infinity, and we consider this limit. But this time we'll have to scale it down by the scalar curvature. Right, scalar curvature times G centered at Pi. And so this sequence of manifolds will converge to a cylinder S2 cross R. So this is not as flat. So this cylinder is a non-collapsed. So easy to see that this Bryan soliton is a non-collapsed. Okay. And so here are some more complicated examples of static gradient solitons that are constructing in some other way, which can be viewed as some generalizations of this rotationally symmetric metric. So the first class would be examples constructed by Evie. And so this, okay, so you can construct some static gradient solitons of this form by taking a doubly warped product. So this first factor is the first warping factor is the k-dimensional sphere, and so this is diffeomorphic to the k+1 dimensional Euclidean space. And then you take another warping factor, which is an Einstein manifold with positive scalar curvature. Now, by some computation using the soliton equation, you can find some proper phi1 and phi2 such that this metric, the metric of this form, satisfies the static gradient soliton equation. So this can be done by solving some ODE stuff. Okay, so this is the static gradient soliton, which is doubly warped product. And even more, you can take a multiple warped product and also show that there are some static gradient solitons of this form. Instead of taking warped product with one Einstein manifold, you can take product over many Einstein manifolds with positive scalar curvature, and this is done by Denson 1 in 2008. So in these two examples, you can check that so they show that this Ricci curvature is always non-negative, but the sectional curvature must be negative somewhere. So this this leads to an open question by Cao Huaidong. And in a survey paper, he asked if there are any non-rotationally symmetric static gradient soliton which has positive curvature operator in dimension n greater than or equal to 4. Okay, so now we're going to we're able to give a positive answer to this question, and this is stated in our first theorem. So it says that so we find such solitons, and we can even show that they have these types of symmetry, Z2 cross OM minus 1 symmetry, and so they have positive curvature operator and they are not rotationally symmetric. So I'm going to give you a picture of these solitons in the end of this part, but that's just move on right now. Okay, so now let's come back to dimension 3 and let's see what do we have about 3D static gradient solitons so far. So now we've known two of them. One is that you can take a product of R and scalar, and then and you get a static gradient soliton. It is collapsed as the scalar is collapsed, and the asymptotic cone. So by asymptotic cone, I mean that you can take the blowdown of the manifold. So this is a notion for the asymptotic cone. And as we blow down the metric, then you see that it is the tangent cone, or yeah, maybe this makes more sense, is a half plane. Because the blowdown of scalar is a half is a ray, and so overall this asymptotic cone is a half plane. And then you have, of course, the third-dimensional Brownian soliton, which is non-collapsed, and the asymptotic cone is simply a ray, which is a metric cone over a single point. Okay, so there are some nice classification results of three-dimensional static gradient solitons under additional assumptions. That with these additional assumptions, they are able to show that the soliton is either the first one or the second one. Okay, so the first condition that you can add is that the non-collapsing, and it is a trivial result by Brundtler, which says that the Brownian soliton is unique such solution. Okay, and so with this, he could even show that the Brownian soliton is also the unique ancient non-collapsed solution in dimension 3. Yeah, that is non-compact, of course. Otherwise, you will have the 3-sphere. Okay, so that is first classification. And then we know that if the curvature of the static soliton decays, then it's not hard to show that it will decay at least linearly. And we know that the Brownian soliton actually have a linear curvature decay, right? And so it is a result by Dan and Drew says that the Brownian soliton is unique such soliton. So if you assume the linear curvature decay, then you will have the Brownian soliton. Okay. And in the other, and on the other hand, if the curvature decay is faster than linear, then you have the first type of solution, but it has to be, you have to take some non-trivial quotient of this R times scalar, because the curvature along this R in this soliton does not decay. Okay, so this is a result by Montagnier and Salnon 1. So this curvature assumption is that faster than linear decay. And there's another condition that can be added and lead to the same conclusion, which is that so this Cotino and Monticelli and Monticelli, they assume that if your scalar curvature decays this much fast, so this limit is equal to 0. So this does not hold in a Brownian soliton, because you can easily check that in the Brownian soliton, this scalar curvature decreases like 1 over R, and the ball of this and the ball has the volume of the R ball increases like R squared. So this volume, so this limit will stay positive as R goes to infinity. Right, and they can show that if this limit is 0, then it has also to be a non-trivial quotient of R times scalar. Okay, so I think I'm going to only mention these classification results. And so now it is a natural question to ask if there is any new static gradient soliton in dimension 3 that fails all these assumptions. So that is neither the Brownian soliton nor the R times scalar and their quotients. And actually, this is a conjecture by Hamilton, and he conjectures that such soliton exists, and he called them the flying wings. So they're called the flying wings because they have the shape of a flying wing because that's by definition, it's a static within soliton, and of course it has positive curvature, and it's below them. The asymptotic cone is a sector. So this sector, it has angle strictly between 0 and pi. So in this sense, you can view these flying wings as some interpolation examples between the brine soliton and R times scalar, because we know that the borderline cases corresponds to the examples. Okay, so now our second theorem confirms this conjecture, and we find such flying wings, which are Z2 cross O2 symmetric. So again, I owe you some pictures that I'm going to show you in the end of this part. Right, okay, so now this is the 3D flying wings, and if you generalize this concept a little bit, then we can say what is a higher dimensional flying wing. So here is our formal definition. So we say that in general, an n-dimensional flying wing is some static gradient soliton with positive curvature operator, such that its asymptotic cone is a metric cone over some geodesic ball in this n-1 dimensional sphere of curvature equal to 1. Okay, so as you will see that this geodesic ball is a generalization of this interval. So this interval, you can view it as a geodesic ball in S1 of radius theta over 2. So theta over 2 is between 0 and pi over 2. Okay, so this if you define the flying wing in this way, then in dimension 3, you get back to Hamilton's flying wing. And in higher dimensions, we also proved that such flying wings exist. Okay, and even more, we can show that these are OM-1, OM-2 cross O2 symmetric solitons. Okay, so again, I'm going to show you pictures in the end of this part. Okay, so now I want to take in the next few slides, I want to also review some known results about flying wings in mean curvature flow. So flying wings is also a very interesting example in mean curvature flow, and they have been constructed long ago, and there are many more fruitful results in mean curvature flow than it has in Ricci flow. So I'm going to see this at the, okay. So the mean curvature flow is another type of geometric flow, and it's described by a family of immersions into our n+1 dimensional Euclidean space by this family of immersions, x parameterized by t. So I denote this by the image of this immersion m sub t. So if this is so it is a mean curvature flow if it satisfies this evolution equation. It evolves by this mean curvature vector. And also there are self-similar mean curvature flows, and the counterpart of our static gradient Ricci soliton is called a translator. Okay, so the translator, as definition, is that it's a mean curvature flow which evolves by translation. So so that means that the image of this immersions evolves under our translating satisfy this translating equation for some fixed vector E. So usually we'll assume that this E is a non-zero vector, because otherwise, if it is 0, then we'll be only looking at the minimal surface. So we'll assume that it is non-zero, and we'll normalize it, and usually we will pick this translating vector E, this velocity vector, to be equal to this one. And so now being a translator basically means that the normal component of this velocity is equal to this mean curvature vector. Okay, so now this is a translator, and it is a counterpart to our steady gradient solitons, steady solitons. And then among these translators, some of them are even nicer, and these are translators that are given by a graph of a function. So we call them the graphical translator or translating graph. And so now we can talk about what is a flying wing. So flying wing, it is a convex graphical translator if this function u is defined in a finite slab. So it's definition domain of this function u, whose graph is a translator. So its omega is contained in a finite slab, and then it is a flying wing. Okay. So I'm going to show you the picture in the end. So okay, so for the mean curvature flow flying wings, there are many nice results. And the first one is the existence results. So first, it was proved by Wang Xujia that there is for any dimension n greater than or equal to 3, you can find a flying wing that is contained in a finite slab. Sorry. Okay.
I'll show you the chat.
Oh, okay. Okay. So right. So a slab means that. So for example, if n is equal to 2, then this omega is contained in R2 plus is contained in R3. And so by contain a finite slab, I mean that, okay, so let me just draw a picture. So this is R2 cos 0. So this is a finite slab. Well, y has absolute value bounded above by some constant, and x is any real numbers. Okay, so right, so omega is such a domain across, of course, z equals to 0 in this case. Does that answer your question? Okay, thanks. Okay, right, and so right, so now first Wang Xujia proved that given no, not given. So you can find a flying wing that is constructed that whose domain is in a finite slab, like in this picture. And then this existing results is even is extended and completed by Hoffman, Neyman, and Martin White, and independently by Borney, Lamford, and Tinaglia. So they were able to show that given any slab of a width bigger than equal to pi, you can always find a flying wing contained in that slab. Okay, so this is their theorem. So this can be done for any dimension n greater than or equal to 3, and so you can, yeah, for any prescribed width, you can find such a flying wing with that width. Okay. And even nicer, you can show that such flying wings is even unique, and this is done in dimension 3 by Hoffman, Eman, and Martin White. So they were able to show that for any given slab, you can find one and only one flying wing contained in that slab, but not contained in any smaller slabs. Okay, so but this I think this is only shown in dimension 3 till now. Okay, and so now we know that by this convexity theorem of Brook and Xiao, where they showed that any three-dimensional translator is, any translator contained in R3 is actually convex. So now this theorem of Hoffman, Neyman, and Martin and White leads to the following classification result of all translating graphs in R3. So the first class is the flying wings contained in a given slab with the width b greater than equal to pi. And then the second type is the Grim Reaper surface, which we'll see is how it looks like in a second. And then a tilted Grim Reaper surface, and then the bow soliton. The bow soliton is a rotationally symmetric soliton, which looks like our Brown soliton in Ricci flow. Okay, so now this is the result of mean curvature flow flying wings. And so next, in the following diagram, I'm going to compare these results with what we know in Ricci flow. And you'll see that there are a lot of similar properties between these two objects, even if they are different geometric flows, and they okay. So in this diagram, in the second column, we have some convex graphical translators that is contained on Rn. And on the right-hand side, the third column, we have the n-dimensional steady gradient Ricci solitons with a positive curvature operator. Okay, so now let's get started. Now let's start to compare them from n equals to 2. So in this case, the translator is a so-called the curve shortening flow, and here and it is called a Grim Reaper. So it's a such curve, and it involves like this under the curve shortening flow or the one-dimensional mean curvature flow. Okay, so this is a Grim Reaper, and it looks very much like our cigar soliton. So cigar soliton, it also has bounded weight at infinity, like the Grim Reaper. So these Grim Reaper and cigar solitons are important for higher dimensional translators and the solitons, because we will see them as the asymptotic translators in higher dimensional collapsed solitons. Okay, okay, so right, so in n equals to 3, dimension 3, we are going to compare these two solutions regarding on their collapsedness. So there are two types of solutions for both of them. If you consider the collapsed solutions, then you get these flying wings constructed. So you got this Z2 cos O2 symmetric flying wings. So it looks like this. And if you take a sequence of points going to infinity along the edges of the wing, and you take a limit of this pointed manifold, and then you get a Grim hypersurface, or actually a tilted Grim hyperplane, a tilted Grim hypersurface. Okay, so now you see the Grim Reaper as an element in this kind of asymptotic behavior. So this is the collapsed examples, and then for the non-collapsed examples, you have the bow soliton, and it is shown by Haushofer that it is the unique such soliton if you assuming this non-collapsedness. This bow soliton, as we explained before, it is rotationally symmetric, and it opens up as like the square root of r. R is the distance to the tube, right? So now we're able to show that there's something similar in the side of Ricci flow, and here is our second theorem. So it says that we can also construct some similar stuff. So it's called that is known as a flying wing, and it is also have the similar asymptotic behavior at infinity, right? So now if you choose a sequence of points going to infinity, again along the edges of the wing, then you see that the manifold will converges to R times scalar. Yeah, so it will split up a line and so the converges to R times scalar. So right, so this is the flying wing. And in the non-collapsed case, Brundtler shows that the unique such soliton is a Brine soliton. And yeah, so it has the same picture as the ball soliton. And for higher dimensions, again, we're dividing them into the collapsed ones and the non-collapsed ones. And again, for the collapsed ones, we have those flying wings. So as before, so like in dimension 3, this here you see an interval which so this grim reapers is parameterized only by 2 points, but here it is parameterized by a circle because the dimension gets higher. It is parameterized by a circle in dimension 4 and parameterized by a 2-dimensional sphere in dimension 5, and so on and so on. So this is how these flying wings look like. And also, if you take a sequence of points going to infinity and take a limit, then you will again see a grim hypersurface, a tilted grim hypersurface. And this is what we can show now in the Ricci flow side. So we can show that such flying wings are also available in Ricci flow, and also that in the level set you will see a bunch of scalar soliton, and then in dimension 3 they are parameterized by a circle. Okay, so that is a higher dimension flying wing. It is how they look like. And in the non-collapsed case, in this side, you have for the main curvature flow, you have this Z2 cross O and -1 symmetric translators, which is also constructed by Hoffman, Eman, and Martin White. So here is how this translator looks like. So first, they are Z2 symmetric, so you can reflect this soliton and still get itself. And then this O and -1 symmetry means that these fibers are the n-1 dimensional sphere. Okay, so now right, so they have different asymptotic behavior as the flying wings. So by this I mean that if you take sequence of points going to infinity, and then this time you will see another type of splitting. So that was split up a line again, but after proper rescaling, you will see the limit is R times the Brine soliton. Oh, sorry, the ball soliton. Okay, so it's not the Grim Reaper anymore. And so now our theorem 1 says that you can also construct such non-collapsed examples for Ricci flow for static gradient Ricci solitons, right? So again, so this limiting translator is the limiting solution is R times the Brine soliton, n-1 dimensional Brine soliton, and it looks very much like the examples constructed by Hoffman, Eman, and Martin White. Okay, so that's the main result. Okay, so now let me come to the second part, and then I'm going to show you how we construct these solutions. Okay, so they are so in this theorem we show that for any dimension n, we have if you have any constant between 0 and 1, then you can always find a Z2 cross O and -1 symmetric static gradient soliton with positive curvature operator satisfying this relation at the critical point of the potential function. So this λ1, λ2, λn are the n eigenvalues of the Ricci curvature. So λ2 and λn are equal because of the symmetry assumption. Okay, so Right, so this is how the theorem states. Okay, so now I'm going to show you the outline of the proof. So for simplicity, we'll only focus on n equals to 3, but for the higher dimensions, it basically follows the same line. Okay, so also to start, we're going to find a sequence of smooth family of metrics on these two. And they have the following they satisfy the following 5 conditions. Okay, so to make this easier, I'm going to show you in the right hand picture, so you can check with the left hand side. Okay, so to construct this such metrics, we start by constructing a sequence of ellipsoid, like on the right hand side. Okay, so now we can choose this ellipsoid in a proper way such that their curvature is always bigger than 1. The Gaussian curvature is always bigger than 1, and their diameter converges to pi. So I hope you can agree with me that these 2 conditions can be satisfied at the same time. Otherwise, we can just do some computations. Okay, so now after you constructed this sequence of metrics, with each one, you start a Ricci flow on this manifold, and then it will shrink. It will shrink to a round sphere along the Ricci flow. So you can do some proper rescalings, and now your final time slice will be a round sphere, and its volume is relatively comparable to your initial metric. Okay, so here's the Ricci flow that you run from the right-hand side to the left-hand side, and you do some rescalings. Right, and so you can do it in such a way that this sequence of metrics, they are a sequence of shrinking spheres, and they have smaller and smaller volumes. And even more, we can require that the volume of these metrics in between uniformly converge to 0 as I goes to infinity. Right, so this can be done. Okay, so now the reason why we want the volume to converge to 0 and can be seen by the following compactness lemma. So I think I don't have time to run into the detail of the proof, but okay, so let's just skip this lemma. Okay, right, so now let's see. We have constructed this family of metrics, GIU. So now for each GIU, we can use the Rayleigh's result, de Rayleigh's result, and we can find a unique expanding gradient soliton that has positive curvature operator. Its asymptotic cone is given by the metric cone over this metric GIU. Okay, so because we know that this GIU, it has curvature greater than 1. So as we explained before, you can find such an expanding gradient soliton, and it is unique. So now by some compactness argument, they can show that since the volume of GIU goes to 0, so this is our last condition in last slide. And so now you can show that this sequence of expanding gradient solitons will converge to some static gradient soliton. Okay, so now if you do this for this different sequence of expanding gradient solitons, then you get different of static gradient solitons in the limit. Okay, so now for example, you choose this sequence which corresponds to the shrinking sphere, the shrinking to sphere, then the limit is a Brownian soliton. So this quotient is equal to 1 because it is rotation symmetric. And if you do this to the other sequence, the sequence of ellipsoid, which we start with Ricci flow, and then you get the limit is r times scalar, because their diameter converges to pi. So in the limit, you will get an r line splitted. Okay, so right, so in this solution, you have this quotient equal to 0. So now by some continuity argument, you can find for each large I, you can find some number that satisfy this equation exactly. So this alpha is chosen and fixed before. And so now for this particular sequence, you run the compactness argument again, and then you will get another static gradient soliton. And this static gradient soliton will inherit this, this relation. And so this will be the static gradient soliton that we want. And so this is the theorem. Okay, so now this theorem has given us a lot of non-rotationally symmetric static gradient solitons with positive curvature operator. So they can be constructed for any dimension n equal to n greater than equal to 3. And in the last few minutes, I want to show you that in particular, in dimension 3, these solutions are indeed Hamilton's flying wings. So we'll exclude the possibility that they look like a ray in this in infinity. Okay, so this is our goal in the last part. Okay, so right, so before we show that it's this 3D static gradient solitons, we constructed a flying wing. So we're going to first establish a quantitative relation between the limit of the scalar curvature at infinity and the asymptotic cone angle. Okay, so let's say if you have an asymptotic cone angle equal to alpha, well, the alpha can be any number between 0 and pi. So when it is equal to pi, it is r times scalar, and when it is 0, yeah, we don't know. It could be the Brownian soliton or something else. Then okay, so this alpha is asymptotic cone angle. In this gamma is basically the edges of the wing, which is more rigorously a complete geodesic fixed by the O2 action. Then we can show that there is a quantitative relation between these two objects. So this limit is uniquely determined by this asymptotic cone angle. Okay, so right, so you can easily check that when alpha equals to 0, then this limit is 0, which means that if your asymptotic cone is a ray, then your curvature has to decay. Okay, right. And in all other cases, if it is not a ray, then your curvature does not decay. Okay, so here's something that we can see directly from this statement. Okay, so next I'm going to show you how we can use this relation to show that this the flying wing conjecture is actually true. Okay, so so I hope to show that if the asymptotic cone is a ray, then it has to be asymmetric to a Brownian soliton. Okay, so now here's a proof. If it is not a Brownian soliton, let's assume this is not a Brownian soliton, then what we can show first is that it has to dimension reduces to a scalar soliton along the edges of the wing. So by dimension reduction, I mean that I've said this a few times before. So if you take a sequence of points going to infinity and rescale it by the scalar curvature at the tip at this point, and then you will see that the limit is r times the scalar soliton. So this is always true if your soliton is not a Brownian soliton, and you can prove this dimension reduction. Right. So let's assume this is true, and then I'll fix some notation. So this is a gamma, which is the edges of the wing, and then we're going to choose another geodesic, a little gamma, which is fixed by the reflection, the Z2 action. And so, and then we also want to write down the metric as the vector product metric. So this theta is the parameter of the S1 fiber. And so we know that this is a warped product metric, so we have a Killing field given by partial of theta, and so now you can show that this so now you can show that if using the Killing equation, you can do some computation and you can put the following two equations. Okay, so what I'm going to see, maybe I'll just give you a very brief outline this. Okay, so now let's get back to this picture and do this very quick. So I'm going to look at the two quantities. The first quantity I want to look at is which I called H2S. So S is the distance from this point to the tip. So H2 is the length of the S1 fiber at this center geodesic. And another quantity I want to look at is H1 of S, and it is the distance to the edges of the wing. Okay, so now using the soliton equation and some other stuff, we can establish some relations between H1, H2, and the scalar curvatures along this middle geodesic. So the upshot is that so we have the following three things that are important. So first, you can show that you can have a rough scalar curvature upper bound, and then you can show that H2 divided by H1 goes to 0. So this is a direct consequence of the dimension reduction because it converges to the scalar. So the quotient has to be smaller and smaller. And the last one is another relation between H1 and H2. So now combining these few things in this equation that we derived using the Killing field equation and the soliton equation, we can actually show that H2 has this upper bound. So now this is a good thing because this is not satisfied in the Brownian soliton, because in Brownian soliton, the H2, which is a fiber of this one fiber of the S1, the length of the S1 fiber increases like a square root of S, right? So this is a good thing. And then we're going to replace the second lemma by our new estimate and do some bootstrap argument. So this time you will see an even nicer upper bound on H2. And so this will give you that H2 is bounded above by a constant. And so we're basically done because H2 is bounded at infinity, which basically tells us that this curvature does not decay along the edges of the wing. Okay, so now the curvature does not decay, so we can use our previous relation between this limit and the asymptotic angle. So that relation tells us that if this is non-zero, then your asymptotic angle is not zero. Okay, so now this is a contradiction because we're assuming that the alpha is zero in zero, right? So now we can now by this theorem, you see that all the 3D static wind solitons we constructed before are indeed flying wings. So they have positive asymptotic angles. Okay, so I think I will stop here, and thanks very much for your attention. Thank you.
Thank you very much, Yi. Are there questions? Yeah, there is a question by Alex, who is in the room actually.
Okay. Anyhow, to characterize these flying wings without any symmetry assumption. Yeah, so right, so actually I think that all these flying wings Okay, so I think you can definitely talk about flying wings without symmetry assumptions. So you can just define them as 3D static gradient solitons whose blowdown is a sector, and in that way you don't have to say anything about the symmetry. But I think my hope is that to show that any such solution, any flying wings without the symmetry assumption is in fact still a swan symmetric. Yeah, and I think this can be done. Yeah. Does that make sense? Yeah, thanks.
Another question in the chat.
Okay, I saw that. Is there a compact tension solution which has positive curvature and is collapsing? Okay, yeah, thanks for the question. Yeah, it's also a very good one. And yes, right. So let's just focus on dimension 3. And the answer is yes, because right. So there is you can imagine that there are ancient pancake, and I've constructed them, but this is not a result on archive yet. So this ancient pancake, you can think of them as a counterpart to the ancient pancake in mean curvature flow. So maybe I can show you how they look like in this picture I drew. Wait. Okay, so here, the ancient pancake, they are, so it looks like the level set in this flying wing. So right, so this is a 3-dimensional flying wing in a 4-dimensional sorry, this is a 3-dimensional ancient pancake in a 4-dimensional flying wing. Right. So this is one example that which is a compact ancient solution that is collapsed and has positive curvature. And maybe I think maybe you can also construct other not rotationally symmetric compact solutions. As for you can maybe you can show something like this. So you can glue up some flying wings. So here you have a flying wing. Here's another, and you can glue up these 5 flying wings to get a compact Ricci flow. And then it is not an ancient pancake because it is not rotation symmetric. But I think such solution might still exist, but I'm not sure exactly. Yeah. Yeah, thanks.
More questions? Okay, I guess people are tired a little bit. So we thank you very much for this talk with a very nice example. And hopefully we'll meet again tomorrow morning, one morning for us, and expecting for more beautiful videos. Thanks.
Yeah,
thanks.
yeah.
Have a nice
Thanks
a lot.
Yeah, thanks very much.
Right.